Hello. Today we're going to talk about finite sums and sigma notation. So sigma notation uses this Greek letter sigma, this capital E looking thing that reads as sigma, and it enables us to write a sum with many terms in a compact form. So instead of listing out the n infinite terms, we can write it compactly, nice and small, using sigma notation. So let's break down all of the pieces involved in this sigma notation. We have index values. So in this case, we start at k equals 1. K starts at 1, and the index ends at some nth k value, right? So we're going from 1 to 10, or 1 to 7, or 1 to even infinity, all right? This Greek symbol for sigma, the Greek letter sigma, this represents our summation symbol. And then a sub k, this will be the term or the formula we use to find each term. So it's going to essentially represent our nth term, and we'll plug in our index values, k equals 1, k equals 2, k equals 3, repeatedly and add up all of those terms until we get to our nth term. So we talk a lot about sums in Calculus 2. We get into infinite series, sums, and sequence. And it becomes important to us in our understanding of divergence and convergence. So just to help us understand this sigma notation a little bit more, let's look at developing that sigma. So in this case, I am finding the sum of 11 terms. And you'll notice that all of these 11 terms look like some value raised to a power, 1 squared plus 2 squared plus 3 squared. So they're all the index value in ascending order, 1, 2, 3, 4, 5, etc. They're the index value squared. So our summation notation, this summation represents what we're looking at here. And the summation notation is far more compact than listing out all of those terms. And say, what if we were finding the sum of 100 terms? You really wouldn't want to list those out. So what we're going to do is we're just going to make sure we kind of understand what sums are and how to use them, because they build towards our fundamental theorem of calculus. So now on this screen we have just some examples of sigma notation and what it looks like when you list out the terms, and then what the actual sum value is if we were to add up the terms. Okay, so we're just going to analyze these. This first one, we're going to have 5 terms. We're going from k equals 1 to k equals 5. And my terms, I just plug 1 in for k, then 2 in for k, then 3 in for k, 4 up to 5, because 5 is where my value ends. So if I add up all of those terms, I end up here with 15 as my sum. The next sum we're looking at here is a alternating sum or series. Okay, so when you think about raising -1 to a power, say raising -1 to the first, it would be, or rather, it would remain negative. However, if I were to raise this to a squared power, an even power, it's going to turn positive. So my summation in this series, we have 3 terms. We're going from k equals 1 to k equals 3. And I'm going to use this function, plugging in 1, plugging in 2, plugging in 3. So that gives me 3 terms that I can calculate. You'll notice the second term, which was raised to an even power, is positive. And if I were to add those up, I get -2 as my sum. My third series or sum here, we just have two terms because we're going from 1 to 2. So wherever there's a k, I plug in 1 and 1, and then on my next term I plug in 2 and 2. Adding these two terms together gives me a sum of 7/6. And my last summation or series here, I want you to notice that we're starting at k equals 4 and going to 5. And that's, again, only going to give us two terms, 4 and 5. And so I like showing you this one because I want you to notice the index doesn't always start at 1. Oftentimes they'll start at 0 or 1, but we can have the index start at any k or n value. So plugging in 4 and plugging in 5, evaluating, we get the sum of 139/12. So hopefully you have a better understanding now of what summation notation is. So let's do an example. We are going to express this sum using sigma notation. The formula generated varies based on the lower limit of summation that is chosen. So as I said on the last example, generally it's simplest to choose k equals 0 or k equals 1, but you could start with any integer. So if I were to do this summation, and I'll say let's let k equal 0, then the formula, my sigma notation, might say, well, k equals 0. 0, this is my 0th term, my first term, second, third, 4. So if I let k equal 0, that means we're going from 0 to 4. And then we need to come up with a formula that would give me those values. So 2k plus 1. And so if I look at plugging in 0, 2 times 0 plus 1 gives me my first term, 1. 2 times 1 plus 1 is my second term, 3. 2 times 2 plus 1 is my third term, 5, and so on. So you see it's giving me my terms in order. Okay? Now, how would this be different if I said, well, let's let k equal 1? So suppose I chose this differently and I said choose k equal to positive 1. So if k equals positive 1, how does that change my formula and how does that change my summation notation? So in this case, we would start at k equals 1. And if this is my first, second, third, fourth, 9 would be my fifth term. So what would my formula be that would give me 1 for my first term here? And this changes my formula a little bit for my nth term or my kth term. This would be 2k minus 1. And you get better at determining these formulas with practice, but it's, a puzzle or a game to try and figure it out. So if I were to look at this and check this out, k equals 1, that would be 2 times 1 minus 1 gives me 1. 2 times 2 minus 1 gives me 3. 2 times 3 minus 1, 5. 2 times 4 minus 1, 7. And 2 times 5 minus 1 gives me 9. So this formula, when I'm going from 1 to 5, gives me that exact same summation. And just to expand further, let's choose another k value. How would this differ if I chose k equals, say, 2? So looking at defining this sum for starting at k equals 2, my lower bound or my initial index. So if I change this to go to 2, then that would mean 2, 3, 4, 5, 6. 6 would be the fifth number following that. And my formula here would be 2k minus 3. Okay, so there's no one exact right answer. It just depends on where you start. And you see that my indices, my index values vary, and then also my formula for the nth term varies as well. All three of these summations give me the exact same answer for my sum. And all three of these would come together and equal 25. So they all are exactly the same. They just look different. So we have algebraic rules or properties that apply to finite sums, just like we have rules for limits. So like for our sum rule here, it says the sum of some term A plus some term B. Well, the sum of the terms A plus B is the sum of A plus the sum of B. Same for difference. You'll notice with a constant multiple, when you're multiplying by some constant C, you can pull that in front of the sum. And then if you have the sum of a constant, you will have n, your upper index or upper bound value on that sum, n of those constants, so n times C. So more or less the same as, the properties of algebra on limits or on derivatives, those still all apply to sums. And notice here we're talking about finite sums, which means there is a specified nth value, something that is quantifiable. Eventually we start talking about infinite sums. So how do you sum up all of the numbers to the infinite term, the never-ending sum? And then we get a little bit into the concept of convergence versus divergence. Does it converge or diverge? Can we calculate that sum? So let me just demonstrate some of these algebra rules. So for example, if I gave you the sum as k starts at 1 and goes to some nth value of 3k minus k squared. So applying this, I could break this down into littler sums. Okay, so that 3, that constant multiple 3 could go in front of the sum, and this would be the sum from k equals 1 to n of k, minus, we could separate those by using our difference rule, k equals 1 to n of k squared. So we're not really solving anything here. We're just making sure we understand that we can manipulate these sums when we are solving to simplify things. Another example, if I had k equals 1 to n of negative a sub k. So I just like to point out that that negative is a constant multiple and could come in front of the sum. And my last little property here, we could say k equals 1 to some finite value 3 of k plus 4. So we can actually calculate this since we have a finite value. So this is the same as writing the sum from k equals 1 to 3 of k plus the sum of k equals 1 to 3 of 4. So I used my sum rule here, and I was able to separate this into two sums. Now this first sum, if I plug in 1 and then 2 and then 3, I would end up with 1 plus 2 plus 3. And the second sum, that's the sum of a constant. So sum of a constant, we have 3 terms, and it's just going to be 3 times that constant, which is 4. So in this situation, if we calculate that sum, we end up with 18. So I hope you have a better understanding of what a basic sum is. And you understand how the summation notation works.